Our topic of review today are questions that utilize a table of values. So it's going to be a variety of different topics that we're working with, but the common theme will be a table of values. So here's question 1. A test plane flies in a straight line with positive velocity v of t in miles per minute at time t minutes, where v is a differentiable function of t. Selected values of v of t for 0 to 40 are shown in the table above. So part A, it says use a midpoint Riemann sum with 4 subdivisions of equal length and values from the table to approximate the integral from 0 to 40 of v of t. We want to show the computations that lead to our answers, and we're going to use correct units, explain the meaning of this integral from 0 to 40 v of t dt in terms of the plane's flight. So before I started this, I did a really quick sketch of the table because I think that helps a little bit when it comes to Riemann sums. So we want to do a Riemann sum. We're going to do a midpoint Riemann sum. So we're going to use the area of a rectangle. So area equals length times width. And we want to use 4 equal subdivisions. So if we're going from 0 to 40, an equal subdivision would be of length 10. So I'm just going to draw that in. So here's 1 subdivision, 2, 3, and 4. The fact that we're using midpoint means that we're going to use the midpoint value for the height of our rectangles. So I'm just drawing in my rectangles. So I want to find the area or the sum of the areas of those 4 rectangles. So here's what it's going to look like. 0 to 40, v of t dt is approximately, they each have the same width of 10. And then I'm going to take my individual heights. Now my individual heights are the values in my table for velocity at the 5s. So 5, 15, 25, and 35 are my middle values. So I'm going to use 9.2 plus 7.0 plus 2.4 plus 4.3. And we get approximately 229 miles. Now the second part of this question says, using correct units, explain the meaning of this integral in terms of the plane flight. And this is the net change in miles flown by the plane from time equals 0 minutes to a time equal to 40 minutes. Letter B. Based on the values in the table, what is the smallest number of instances at which the acceleration of the plane is equal to 0 on the open interval from 0 to 40? So I want to know where is acceleration equal to 0. And I know that acceleration is equal to the derivative of velocity. So really I want to know where must the slope of velocity equal 0? That's my question to myself. So if I look at here, slope of 0, let's think about secant lines. All I have to work with is this table of values. So where would the secant, or the slope of the secant line between 2 points on this table be 0? And that would be where we have y values that are the same. So I notice that we have the same y value for f of 0, or v of 0, excuse me. V of 0 equals v of 15. They both equal 7.0. And v of 25 equals v of 30, which is 2.4. So what that tells me is that if I found the slope of the secant line through those 2 points, that slope would be 0. Now, since our velocity function is differentiable, it means that our velocity function is also continuous. And from that, we can now use the mean value theorem, or more specifically, Rolle's theorem. So here's what I'm going to write. Since v of t is differentiable, it must be continuous. The slopes of the secant lines through 0, 7.0 and 15, 7.0 is 0. I guess I should say the slope of the secant line. The slope of the secant line through 25, 2.4 and 30, 2.4 is also 0. Therefore, by the mean value theorem, there must be a point in 0 to 15 and 25 to 30 where v prime of t equals 0. So my answer is technically 2 times. The minimum number of times is 2. There's my justification. Okay, letter C. The function f defined by f of t equals 6 plus cosine t over 10 plus 3 sine 7t over 40 is used to model the velocity of the plane in miles per minute for 0 to 40. So this is an alternative function that we could use to model our velocity. According to this model, what is the acceleration of the plane at 23? So we know velocity. So if we want to find acceleration, it's going to be the derivative of my f function, which is my velocity model. So using my calculator, I'm going to find f prime of 23. I'm going to type it into the n-deriv button. I get negative 0.408 meters per minute, or miles, excuse me, per square minute. Well, that's all I need to do there. Part D, according to the model F given in Part C, what is the average velocity of the plane in miles per minute over the time interval from 0 to 40? So average velocity means I'm going to use my F average formula. 1 over 40, 0 to 40. We're not doing a velocity function. Technically, it's a velocity function, but we're working with F of t dt. So I'm going to plug that also into my calculator. I get 5.916 miles per minute.